Okay, everyone, welcome back. I hope you're enjoying preparing for your non-Thanksgiving as much as I am. I am going to be available tomorrow for office hours, and then I remind you that the next week we have, after Thanksgiving, we have 2 more classes, Tuesday, Wednesday, and Thursday. And again, I will be available for office hours on Wednesday, and I'll probably be available for office hours throughout reading period and up until before Christmas. At the usual time, Wednesday at 2. Okay, so I want to get into expanding graphs in more detail today. And there's sort of 3 different notions that are closely related. One is non-amenability. One is, let's call it expansion. Another is called property T. And maybe I'll add one more here, which is eigenvalues of the Laplacian, lambda naught and lambda 1. So these are all kind of intertwined, even despite this different sounding names and superficially different looking concepts. So last time we discussed the notion of a non-amenable group. And the original definition was that a group is amenable if it admits a G invariant mean on L infinity. But there was a more geometric definition due to Fulner, which worked like this. We take our group G and we have, suppose it's finitely generated. So we choose a finite generating set S. And then from this data, we get a graph. And the vertices of this graph are the elements of G. And then we connect elements when they differ by a generator. So there's an edge that goes from G to S times G. And then we can forget about the group for a while and just think about graph theory. And in this graph, we have the notion of the boundary of a set A. It is the set of vertices that are attached to A by an edge, but which are not themselves in A. So this was the notion of the boundary of A. It doesn't include the edges, it just includes the vertices. And then from this, we build up a constant, as an invariant of the graph. So let me just call this graph G for abbreviation. And the invariant of the graph is the infimum of the size of the boundary of A over the size of A. This is the graph. It's a sort of isoparametric inequality. And then we say that G is non-amenable if and only if H of G is positive. So in other words, if and only if the boundary of a set is roughly speaking, up to a constant factor, is roughly speaking the same size as the set itself. And of course, this is only interesting for infinite. Oh, I should have said here that of course A ranges over finite sets. So this is the inf over A contained in the vertices of G, and of course finite. And if the graph were infinite, then you could, if the graph itself were finite, you could just let A be all the vertices, there'd be no boundary, and it would definitely be amenable. Okay, so now comes the notion of expanding graphs. And an expanding graph is similar to, has a similar definition, but an expanding graph is actually not a single graph. It's a sequence of graphs. So what we want to find is a sequence of graphs that have a uniform bound on this constant h of g. They somehow look like larger and larger pieces of a non-immutable graph. So we say a sequence of let's say, graphs Gn is well, actually, the terminology is always kind of awkward because it's not the individual graphs that are expanding, but it's the sequence of the graphs that are. So we say graphs Gn form an expanding sequence if, well, first, the number of vertices should go to infinity. And second, but it should always be finite. So I should say finite graphs form an expanding sequence if the number of vertices goes to infinity, but the degree of Gn is less than or equal to some constant that doesn't depend on n. So for example, these might all be trivalent graphs. They have at most 3 edges coming out of each vertex. And then the third property is that some analog of this isoparametric inequality holds. So let me call this H0 here. And what we're going to require is that H1 of Gn is greater than or equal to some constant greater than 0. There's a uniform bound on the isoparametric inequalities for these graphs, where H1 will be defined in almost the same way. So let me just modify this definition. So H1 of G is the inf of this ratio over sets A contained in the vertices of G, where this cardinality of A is less than or equal to half the cardinality of G. So you take a set that comprises at most half the vertices, and then it has to have a reasonably large boundary compared to the size of the set itself. So what we see is this H1 is a substitute for H0 in the case of a finite graph. So you have this vast but finite graph, and it feels kind of non-amenable as long as you don't look at it at a scale that's comparable to the diameter of the whole graph. Okay, so these, as you can see, there's some tension between these inequalities. We want the boundaries of sets to be big. One way to do that would just be to attach every vertex to a lot of others. For example, you could take the complete graph on a given set of vertices, but then the degree would be much too large. So the interesting things about these graphs is that they have exponential growth of balls, they have relatively small diameter, and yet the degree at each vertex is small. So as I mentioned, these graphs are they're like small worlds. And they have all sorts of interesting applications as both models for social networks and spread of disease, as well as in computer science for designing robust connection systems that are difficult to disconnect. Okay, so I think you can see there's some relationship between non-amenability and expansion, and it goes through this Fulner condition definition of amenability. Okay, so what I'd like to do is describe some concrete examples of expanders and relate this quantity to something that's more systematic and less combinatorial, namely the eigenvalues of the Laplacian on the graph. So that's going to bring us in this direction. And then non-amenability, I'll remind you there was yet another definition of non-amenability, which was that a group is non-amenable if the action of G on L2 of G has no almost invariant vectors. And we will see that if you replace L2 of G by an arbitrary unitary representation of G, you're led naturally to something called Kazhdan's property T. And property T will also allow us to produce expanders. And on the other hand, we'll also be able to analyze these eigenvalues in the case of manifolds. And so if we know manifolds where we can control the spectrum of the Laplacian, that will also lead us to expansion. Okay, so I want to try to address in a linear way this somewhat nonlinear sequence of interconnected ideas. So the next thing is to discuss the Laplacian. Now, so the Laplacian on a graph of G. So let me first say more systematically how we describe a graph. So this graph G has a set of vertices, which I'll just denote by V. And then there's associated to this an adjacency matrix. And this matrix records for any pair of vertices Aij the number of edges from I to j. And I should emphasize that this is an undirected graph. So the edges don't have arrows on them, and edge from I to j also gives one from j to I. So of course, these are integers, and they're greater than or equal to 0. And I should emphasize that if you add, for example, Aij is equal to 2, here I and j are vertices, I should say. This is the indices of this matrix are the vertices of G. If I and j is equal to 2, it just means we have two parallel edges going from vertex I to vertex j. If you have a diagonal element, which is equal to 1, this means that you have a loop at the vertex I. So we do allow parallel edges and loops so that we can deal with general adjacency matrices. And then we define the degree of the ith vertex to be, of course, the sum of the edges associated to it. So it's the sum over j of Aij. The one nuance that's slightly, one has to take slight care of here is that if you're going to interpret a diagonal element as a loop, then the degree of this vertex is actually equal to 1, because there's only one entry in the associated matrix. And that turns out to be a good convention for the Laplacian, which we're about to introduce. Okay, so now this graph is said to be deregular if the degree di is equal to d for all I. In other words, every vertex has the same degree. It might be, for example, a trivalent graph like this, etc. Every vertex has the same degree, and in the cases that come about from groups, this will be automatic. It will be built into the construction. And then we define an operator called the Laplacian from functions on V to itself. But since it's, I'm going to call it L2 of V to L2 of V, just because we want to be able to use things like the inner product and discuss whether or not this operator is self-adjoint. So here, of course, V is just a finite set, and the norm of a function on V squared is just the sum of its absolute value squared. Okay, so how does the Laplacian work? Well, it's going to give us some sort of average of the derivatives of f in all different directions. So the definition is the Laplacian of a function f at a given vertex I is the sum of f of I minus f of j over all edges in the graph from I to j. Now, why is this a reasonable definition for the Laplacian? Well, the idea is that if you were to build a graph, say, based on a checkerboard grid, then the edges in the graph would be like the coordinate directions with plus or minus signs. And then each of these differences here would contribute to the Laplacian at this point. So there would be a d here, there would be a d here, a d here, and a d here. There would be 4 terms, each of which gives the directional derivative of this function f in going up or down to the right and left. And
is there a square?
Yeah, sorry.
Is there a square? Fi minus fj square?
You can imagine it's a square, but it's a graph.
I mean, if in summation fi minus fj, then do we square it?
No, not at all. It's a linear operator.
Okay.
Okay. This is a linear operator, and one way to think of it is it should be analogous to the operator, which is the ordinary Laplacian on Euclidean space, which is except with a minus sign. So it's analogous to this operator minus the sum of d squared f dxi squared from 1 to n on Rn. So the idea is that this difference here is like the derivative of f. And this is also like the derivative of f in the x direction. And so the difference between these two is like the second derivative. So one way to approximate the second derivative of f at a point is you look at the difference between the two first derivatives, which gives something like 2 times f of p minus f of p minus 1 minus f of p plus 1. So that's an approximation to the second derivative of f. Although this also occurs with is an approximation to the second derivative with a minus sign, because this is f of p minus f of p minus 1 minus f of p plus 1 minus f of p. And this is like the derivative, this is like f prime of p, and this is like f prime of p minus 1. And so their difference can be thought of as an approximation to the second derivative of f at p, but with a minus sign. Okay, so that's some intuition behind what this Laplacian means. And now, as to the question about should something be squared, associated to this operator is a quadratic form, the Laplacian of FF. And if you calculate this out, you'll find that it's something like the sum of Fi minus Fj squared. The associated quadratic form, in any case, is positive, and it's this kind of formula is analogous to the traditional formula in Euclidean space or on an arbitrary Riemannian manifold, that this inner product is the integral of the gradient of f squared. So later on, if I have time, I'll talk more about the geometric Laplacian, but for right now, I want to talk about the combinatorial one. But this is meant to motivate what this operator does. It compares the value of f to its value at nearby vertices. And so, of course, the Laplacian of a constant function vanishes because all of these differences are zero. And as I mentioned, the Laplacian is a positive operator. It's symmetric because since our graph is undirected, A is a symmetric matrix. And indeed, what is a formula for the Laplacian as a linear operator? It's just D times the identity minus the adjacency matrix. And so in particular, it's symmetric. Therefore, it's diagonalizable on a, I should have said this was going to be a finite graph or on a finite dimensional vector space. And its eigenvalues can be enumerated. Lambda naught is less than or equal to lambda 1 and so on. And the least eigenvalue is always equal to 0 because the constant functions are annihilated by f. And in fact, if the graph is connected, the next eigenvalue has to be positive because any function that's harmonic obviously has to be constant, at least on connected components of G. Okay, so the interesting invariant, the first interesting invariant of a graph from this perspective is the next eigenvalue here, lambda 1. So let's say what lambda 1 is concretely. So I'll remind you that this operator delta in an appropriate choice of orthonormal basis just becomes this diagonal operator lambda naught, which is 0, lambda 1, lambda 2, etc., where all these, where this is an increasing sequence of eigenvalues. And if you want to get rid of the 0 eigenspace, all we have to do is take the complement to the constants. So let's add in here the assumption that the graph is connected. Actually, maybe this isn't even required. So we'll let L2 naught of V be the set of functions f of mean 0. So the inner product of f with 1 is 0, or in other words, the sum of f over all the vertices is equal to 0. And then what is the Laplacian? What is lambda 1 rather? It's the smallest possible value for the ratio between the size of the Laplacian applied to f and the size of f itself. So lambda 1, which is by definition the first eigenvalue after the constant eigenvalue, is equal to the inf over all non-zero functions on the graph of the norm of the Laplacian of f in L2 divided by the norm of f. Because this operator is positive and the eigenvector for lambda 1 makes this ratio equal to lambda 1. If you have components in the other eigendirections, this ratio only becomes larger. Okay. So we have a pretty concrete way of thinking about the least eigenvalue of a graph. And what I want to explain is that this invariant of a graph is very closely related to the isoparametric constant that I just introduced. So, so let me state that as a theorem. So the theorem is that for any graph, lambda 1 of G squared is less than or equal to 2d squared times d plus 1 times h1 of g. And in fact, there are inequalities going the other way, which I won't take the trouble to write down, because what we're mostly interested in doing is finding ways to ratify that h1 of g is small. And what this says is that if you can prove lambda 1 of the graph is small, which is a sort of a problem in linear algebra, then you can prove h1 is, if you can prove that's big, then h1 is big. And that's actually very useful in practice, because if I give you a graph and I now say, take the soup over all subsets of its 100 vertices, well, there's 2 to the 100 subsets. So it's infeasible to look at all of those subsets, but Mathematica in a millisecond will tell you what lambda 1 is of the adjacency matrix for the graph. And then that at least provides a lower bound. Okay, so this is a very useful kind of linearization of the isoparametric constant, and it involves the degree of the graph. This should be thought of as something of no consequence. There's just some constant there which is fixed, because when we're studying expanders, we always fix the degrees of our vertices. Okay, so why should this be true? Well, morally, what we're trying to do is, I erased the Laplacian, well, it will come back. What we're trying to do is find a function on our graph, or on the vertices of the graph, which has mean 0. That's critical. But then we also want its Laplacian to be small. So if we didn't care about its being mean 0, to make the Laplacian small, we would make it constant. But we have to have mean 0, which means it has to be positive somewhere and negative somewhere else. So what we can do is we can try to make it equal to a constant over subset A, and then equal to minus a constant over the complementary set B, and choose these values so that the average of the function is 0. And now the good thing about this picture is that the Laplacian will be 0 if you're in the interior of A. But when you get out to the boundary of A, where you have edges that go between A and B, you'll be in trouble. So we would be in good shape if we knew that there weren't too many edges going between A and B. But now we see that that's what the isoparametric inequality controls. And so if we take a partition of the space V, we can use that to build a test function to put in here for lambda 1, and that will give us this inequality. So let's do that explicitly. So given a partition V is the disjoint union of A and B, and let's say that A is the small side, so A is less than or equal to cardinality B. Notice that this implies that B has to comprise at least half the set of vertices. So B is greater than or equal to B over 2. We do the following. We let f of I be equal to the cardinality of B when I is in A, and we let it be equal to the cardinality of A when I is in B, with a minus sign. Okay, so why did I do that? It's because I wanted to have mean 0. So the sum of f over A will be the cardinality of A times the cardinality of B. The sum of f over B will be the cardinality of B times the cardinality of A with a minus sign. So certainly the sum of f is equal to 0. And that's this picture here of our function f. And then we can also calculate its L2 norm very easily. So the sum of the absolute value of fi squared is equal to the sum over A plus the sum over B. So on the A, the function is taking the value B, so we get B squared times the number of vertices, which is A. And similarly over B, we get a squared times the number of vertices, which is b. So this factors as a times b times a plus b. But of course, a and b were a partition of v, so that can just be written as the number of vertices. And in fact, the number of vertices in b is large. It's at least v over 2. So this is greater than or equal to a times v squared over 2. Okay, so up to a factor, depending on the size of the graph, the norm of this function squared is proportional to a. So that looks good. Now, what about the Laplacian of f? So remember, the Laplacian of f at I is the sum of f of I minus f of j. So this is going to be equal to 0 unless I is in A and J is in B. So in other words, the only terms that contribute to the Laplacian are the terms coming from edges that join A to B. So we have A, B, and then we have the edges going from one to the other. And it's these vertices that will cause a problem. That may cause a problem. Now you'll notice that some of these vertices are in the boundary of A. The ones that are in B but are joined to A by an edge, they form the boundary of A. But there's also problems at these vertices. The ones that are in A, but they're joined to the boundary of A by an edge. So these vertices also potentially contribute to the Laplacian. But each of these is joined to an element of the boundary of A, and the degree of the graph is at most d. So this set of vertices has sides of boundary of A. This set of vertices has sides at most d times the boundary of A. And on each of these vertices, how big can the Laplacian be? Well, in fact, we know exactly what it is because f only assumes these two values. The Laplacian is b plus a, which is v itself. So this quantity is an absolute value. This is equal to plus or minus the number of vertices. So what's the L2 norm of the Laplacian of f? It's the number of vertices squared, because we're squaring the values of the Laplacian, times the number of points, where the Laplacian is non-zero, which is at most d times 1 times the boundary of A. So that's an upper bound for the Laplacian's norm, and here we have a lower bound for the L2 norm of f. And so the norm of f squared, the Laplacian of f squared over the norm of f squared is less than or equal to, and now look, this is nice, these square of the total number of vertices, that cancels out, and we're just left with something involving A in the boundary of A. And what is it? On the bottom, we get the size of A, and then this 2 comes up to the top, and then we have this factor of d plus 1, and then we have the size of the boundary of A. Not quite sure where I got a d squared here. Oh, I'm sorry. So in the Laplacian, each term has size plus or minus d, but there's d terms in the sum because there's d edges coming out of here. So the Laplacian squared is pointwise bounded by d times the cardinality of d. So there's an additional factor of d squared here. In any case, the constants that depend on d are fairly inconsequential. And so the main thing is that this ratio of Laplacian squared over f squared is bounded by some constant that depends on d times the boundary of A over A. And now, all we do is we take the inf over A on this side, and we take the sup over f on this side. And then the sup over f gives lambda 1 of g squared, and the inf over A gives this multiple of the isoparametric constant. Okay, so a good way to ratify expansion is to look at lambda 1. And that's the beginnings of the indication of the interplay between expansion and eigenfunctions of the Laplacian. Okay, so the next thing I want to do is give you some examples of expanders. And there are random constructions of expanders, but what we're going to be interested in are concrete examples that will, in fact, come from Lie groups and lattices. And so everything, all these finite combinatorial objects we're discussing are somehow descendants of the ergodic theory on homogeneous spaces. So to construct examples, let me be a little precise about the graph of a group. And in fact, rather than just having the graph of a group with a generating set, I'm going to let the group act on a set and give that space the structure of a graph, just for a little bit of generality. So let G be a finitely generated group, and we choose a generating set, S. And as you'll see in a moment, it's very convenient to require that S is symmetric. In other words, if we have an element in S, then its inverse is also in S. And now suppose G acts on a set V. We then can form the graph G of Vs. And I'm going to specify this graph by saying what its adjacency matrix is. So Aij is just the set of the number of generators such that when you apply S to I, this is equal to J. So for example, in the case where the group action is free, and the elements of S do not contain the identity, you'll have I, you'll have S dot I, S1 dot I, S2 dot I, etc. On the other hand, this definition also works in the case where the action might have some fixed points. So if S4 happens to fix I, then you'll get a loop if S4I is equal to I. And that will just give rise to a 1 on the diagonal of this adjacency matrix. Okay, so that's a very clean way of describing how a group gives rise to a graph on a set. For this graph to be connected, the set has to be transitive. So we'll generally assume that, so we know that G is transitive on V if and only if the corresponding graph is connected. And we'll usually want to assume that because you see if the graph is not connected, lambda 1 is equal to 0 if it's disconnected. Because you can make a function of mean 0 that's supported on the two different components, and its Laplacian vanishes. So we'll generally want G to be connected. And if G is connected, we might as well think of V as being G mod H for some subgroup H. Because to say its action is transitive is just to say V is a homogeneous space. So we let H be the stabilizer of some point, and then we have the left action of G. And in fact, we'll be interested in the case where H is normal. And when H is normal, then the vertices will be the quotient G mod N, which is just some quotient group. What shall I call it? Well, let me just say this is a quotient. G. Okay, so the point is that once you've fixed a finitely generated group in its generating set, every quotient group gives rise to a graph. And so here are our first examples of expanders. The theorem is fix a symmetric generating set S for SLRZ R greater than or equal to 2. And let GP be the graph of the quotient group SLR over the field with P elements using this finite generating set S. So in other words, SL2R maps in to this group by reduction mod P. It therefore acts by left multiplication on this set. And if we use this finite generating set to describe that action, it turns this finite set into a graph. Then these are a sequence of expanders. So of course, the size of this group is roughly p cubed. So the size of the graph goes to infinity. The number of generators is fixed from the beginning, so the degree is finite. And so the whole thing is about showing that the expansion constants of these graphs, the H1s, the isoparametric constants, are uniformly bounded below. Okay, so that's one set of examples. And what we will find when we ratify these examples, when we verify that they really are expanders, is that the proof is very different for r equals 2 and for r greater than or equal to 3. So I won't give the proof now, but let me say the proof will use what's called Selberg's 3/16 bound for r equals 2. And the case r equals 2 was not the first case was discovered, oddly enough. It's the higher rank cases that came about more naturally first. And it will use Kazhdan's property T for r greater than or equal to 3. Okay, so part of the reason for discussing these beautiful examples is not just the intrinsic interest of expanders, but the way they lead in to these other concepts that are of great interest in their own right and give them some context or interesting application. Okay, so I'd like to draw you some of these graphs, but as I mentioned, this graph, the number of vertices grows like p cubed, even for r is equal to 2 already. So it's a bit of a pain to draw. But there's an even more natural sequence of graphs which arises by letting SL2FP itself act on a set. So in fact, there's not so many small dimensional representations of these simple groups of Lie type, SL2R of FP. And the simplest representations arise geometrically. They come from actions of this group on a set. So what does SL2 naturally act on? Well, we've studied SL2 for half of this course. We know it acts on the upper half plane, the space of geodesics, et cetera, but the simplest thing that SL2 acts on is the circle. And the circle is nothing more than the projective line over the real numbers. So what does this group act on naturally? It naturally acts on the projective line over the finite field with P elements. So the second set of example will be the following. Let GP be the graph P elements. Now, what is the projective line? It's no big deal. It's just Fp itself union the point at infinity. So it's a set with P plus 1 elements. And we want to put edges between elements that differ by the action of some generators of SL2. So what we do is we add edges joining x to x plus 1. That's one of the generators of SL2Z, and to minus 1 over x. That corresponds to the matrix 0, 1, minus 1, 0 in SL2Z. Now, these two matrices are in fact sufficient to generate SL2Z. So
sorry, Kurt, the right-hand side's getting blurry on the board.
Oh.
Or I guess it just got better for me. But
how is it now?
it's better for me now, actually. Okay.
Is anyone having a blurry reception?
It's been like intermittently blurry on the right for a couple minutes.
Okay, thank you. On the right, does that mean this side?
No, the side you're currently writing on.
This side. Okay.
Yeah.
Okay, let me see if how is it now?
It's fine right now.
Okay, let me just make sure autofocus is turned off. Aha. Okay. Hopefully that will stabilize things. Thanks for pointing that out. Oh, I see. There was a power outage in the Science Center actually today, and it probably reset the camera's options. Okay. So anyway, what we do is we make a graph whose vertices are the projective line, which just means they're the elements of the field with P elements plus a point at infinity. And then we draw edges that join x to x plus 1 and x to minus 1 over x. And since these two matrices generate SL2Z, that gives an action of SL2Z on this finite set. And in fact, one can prove from the fact that these guys are expanders, the graphs of the groups SLR of FP, for those to be expanders, perforce these guys, which are even smaller, also have to be expanders. So let me just finish stating the theorem. Then these are a sequence of expanding graphs. Okay, so you might think, how could such a simple object be an expander? I mean, can't I just easily draw a picture of that object? It's very, very concrete. I should be able to just look at it and see that it's an expander. So let's try it for, say, P is equal to 7. So what does FP look like? You have 0, 1, 2, 3, 4, 5, 6, and then we're back to 7. And then we have an edge that goes from n to n plus 1. So those edges go like this. And then there's a little bit of a problem, which is we have infinity somewhere. And infinity is fixed under x goes to x plus 1. So it gets some sort of a loop. And now we put in x goes to minus 1 over x. So we have to throw inversion into the mix. So this part we understand pretty well. And 6 is the same as minus 1. So 6, minus 1 over 1 is minus 1. So 6 and 1 get joined. But what about 2? What is the inverse of 2 mod 7?
Four.
Yes, 2 times 4 is 8, which is 1 mod 7. But you see, it's tricky to determine the inverse of a number modulo a prime. Basically, it involves the Euclidean algorithm. And similarly, 3 times 5 is equal to 1. And so here's our first example of an expanding graph. Now, of course, we need a whole sequence of these. But what you see is that the essence of this expansion comes from this transformation here. This innocuous looking transformation, x goes to 1 over x, is actually a very complicated operator on Fp. If we think of Fp as the integers from 0 up to p minus 1. There's no simple formula for what the inverse is of a given prime. In fact, you can think of this number as being sort of random compared to the number that you started with. And in fact, inversion mod p is used as the basis of certain types of pseudo-random number generators. So the point of this graph, what makes it interesting, is what happens when p is super large. So when p is super large, you have this huge cycle going like this, a huge circle with p minus 1 elements in it. And you have infinity. And this is very far from being an expander. And in fact, the diameter of this set is enormous. If you want to get from here to p minus 1 over 2, well, it takes p minus 1 over 2 steps to get there. Whereas the diameter of an expander is log of its size. So the diameter should be log p. And so what this theorem is telling you is that if you want to get from 0 to say p minus 1 over 2 or something roughly on the other side of the circle, what you can do is go along a little bit on the circle and then you apply inversion, minus 1 over x. And that throws you off to some sort of fairly random point. And then maybe you move along the circle a little more and then you apply minus 1 over x and move a little more and apply minus 1 over x and move a little more. And then suddenly you're close to the point you wanted to reach and you finally reach it. So amazingly, the failure of addition and multiplication to interact in an understandable way with each other mod p, the fact that inversion is kind of a complicated looking function from the perspective of addition, facilitates this expansion and turns Fp into a small world. If you take a prime with 1,000 digits, it'll take you about 1,000 jumps to connect any 2 points in Fp by these 2 simple operations. Okay, so let me just show you concretely what one of those graphs looks like. On a second. Okay, so I took the occasion this weekend to compute P1 of F23. So you see some familiar features. There's infinity, there's 0, there's plus or minus 1. Sorry, I'm not sure if I'm showing my mouse. Okay, there we go. There's 0. That's infinity, 0, plus or minus 1. But then up here, it gets pretty complicated. And that's where sort of the expanding properties become more evident. But notice that this group is, this is a trivalent graph. And with our convention that loops count for only one edge, it's also trivalent at infinity. And here I've computed for some fairly large primes, like 27,449, what lambda 1 is of this graph. So you can see it starts out quite large, and then it seems to get smaller monotonically, but it looks like it's converging to about 0.07. And the theorem is that, well, I don't think we know for sure what the limit is, but we know that it's bounded away from 0. And we're starting to see that experimentally here. And moreover, you can compute the diameters of the graphs. Well, I didn't really compute the diameter because that requires examining all possible vertices. But what I did is I started at the origin and I looked at how large a ball you had to take before you reach the whole graph. So the ball of radius 26 around the origin covers all 27,000 vertices in the case of this final graph here. Okay, so those are some examples of expanders that you can kind of carry around in your pocket, and they're quite concrete and easy to construct. And so our goal will be to find out what is the mechanism that gives rise to these expanders. Okay. So as I mentioned, one of the mechanisms is the Laplacian. And we've already made a little foray into the study of the Laplacian on a graph. And we're going to do this over and over again in various guises. But it's always the same argument. The argument is that if you have a big set with small boundary, it forces some eigenvalue of the Laplacian to be small. So let's go for a moment, step back and talk about the Laplacian on a manifold. Okay, so first, the Laplacian is defined once you have a metric on your manifold. And one way to say what it is you take your a function f. So let's say f for the moment is a smooth function on your manifold. And you take its exterior derivative, that's a 1 form. And then you take its Hodge star. That turns it into an n-1 form. Then you take d of that, that turns it into an n form. And then you take star of that again. And that turns it back into a 0 form. That is a function. So this is one of the definitions of the Laplacian of f. And probably there's a minus sign here. It depends on your conventions for the Hodge star. But what I want this operator to have is the property that when f is compactly supported, that the inner product between the Laplacian of f and f itself is the same by Stokes' theorem as the integral over the manifold of the Laplacian of f squared. So this is something we know well from Euclidean space. In fact, in Euclidean space, the Laplacian is written as the divergence of the gradient of f. And when you integrate by parts, that gives you the integral of the gradient squared.
Kurt, could you turn off the screen share?
Oh, thank you.
Thanks.
Yeah. So the normalization we've chosen makes this into a positive operator. And when M is compact, this operator has gives L2 of M a basis of smooth, an orthonormal basis consisting of smooth eigenfunctions of the Laplacian. But even when M is not compact, one can discuss the spectrum of the Laplacian as some sort of densely defined self-adjoint operator. So this positivity, et cetera, is consistent with the fact that this is also a self-adjoint operator, as you can easily see by this formula. And this operator has a spectrum. So if the manifold were compact, we would define lambda naught of M to be the nth of the integral of the gradient of f squared over the integral of the gradient of f itself. Sorry. We would define lambda naught squared to be this ratio. Just as we did in the case of graphs. So what we're trying to do is, see, this is this gives an inner product on the vector space of smooth functions on our manifold M. And we're trying to find the function f, which minimizes the value of that inner product relative to the existing L2 inner product. So that's the definition of this. I'm sorry, I said this wrong. This should not be squared. See, this is, at least for compactly supported functions, this is the same as the f of the gradient of ff over the norm of f squared. And so if, for example, we were able to achieve, if we had an eigenfunction satisfying gradient Laplacian of F is lambda naught of F. And if it were an L2, then this inner product would just be lambda naught times the norm of F squared. And so this ratio would indeed be lambda naught. So this infimum makes sense whether or not F is compact, and we use it as the definition of the least eigenvalue of the Laplacian, even though there might not be an associated eigenfunction. So we take this as a definition of lambda naught of M. And when M is compact, there is actually an associated eigenfunction. In fact, when M is compact, you can just take F to be a constant, its Laplacian is 0 and lambda naught is 0. So we note that lambda naught of M equals 0 when M is compact. However, there are many examples of non-compact manifolds where lambda naught is also non-zero. And these can't have 0 as an eigenfunction. Sorry, I should say infinite volume. These can't have 0 as an eigenfunction because the norm of the constant would be infinite. So for example, lambda naught of Rn is equal to 0 by this definition. And the reason that's the case is this recurring theme of the isoparametric inequality. For example, on the real line, you can make a function that's equal to 1 from minus n to n, and then it goes down to 0 along an interval of length 1, so with slope 1, and it's 0 everywhere else. And so the norm of the integral of f squared is about 2n, and the integral of the gradient of f is about 2. And so this gives a sequence of functions fn for which this ratio goes to 0. So the bottom of the spectrum of the Laplacian on an infinite volume Riemannian manifold is somehow detecting, again in an implicit way, this isoparametric constant for the manifold. So before we get back to expansion, let me tell you a theorem about amenability. So here's a theorem due to Bob Brooks that M be a compact Riemannian manifold, then lambda naught of its universal cover is equal to 0 if and only if pi 1 of M is an amenable group. Of course, I should say connected here. So pi 1 is well defined. So for example, how do you prove Rn is an amenable group? Using this theorem, what you do is you just observe that if you take Rn, as prove Zn is an amenable group, Rn mod Zn is, if we take this to be M, then M tilde is equal to Rn, lambda naught is 0, and therefore Zn is an amenable group. So this is kind of consistent with our pictures of what amenability looks like. And in fact, the proof of this theorem in one direction is just completely routine. And it's just a way of kind of geometrizing our previous combinatorial notion of non-amenability and Fulner sets. So let me prove this in one direction. So let's see, what direction do I want to prove it in? Let's suppose pi 1 of M is amenable. Let me call this G for shorthand. And now what we do is we choose a smooth polyhedral fundamental domain, a D, for this group acting on the universal cover of M. And this fundamental domain should be compact. That's possible because, of course, M itself is compact. So our picture is that the universal cover in some ways looks very similar to the group. If I draw this domain not too big, then the whole universal cover is constructed by looking at translates of this domain by various elements in our group. So this might be S1b, S2b, somewhere way off here, there's GB. Okay, where the fundamental group is acting on M tilde by deck transformations with quotient M. Okay, so now what we do is we choose a generating set for our group. And what generator shall we choose? Well, let's choose the elements in the group such that they enumerate the translates by D that touch D. In other words, I want to choose as my generating set the finitely many elements in the group that move D to one of these cells that's adjacent to it. So let S, this will be our generating set for G, where, so S dot D is the set of translates of D meeting D. At all, meeting it in a, D should be closed, and so even when something touches just at a corner, over here, S60, it should still count as a generator. So I want that the union of S applied to D gives me a neighborhood of D. It contains a ball around D of some small radius. Okay, so now what do I do? So, I've chosen this generating set S, and now we form the corresponding graph G of GS. Now, since pi1 is amenable, we can find there exists for any epsilon z greater than 0, there exists a finite set A contained in G such that the size of the boundary of A is less than epsilon times the size of A. And now what should we do? All we do is we take A times D. That will give us a bunch of tiles in the universal cover of F. And we define a function, f of x, which is equal to 1 on A times D. And it's equal to 0 on, well, I'm a little bit worried about the boundary of A. So I'm going to let it equal to 0 on G minus A union boundary of A times D. And what's left over? What's left over in between are the tiles in S times A times D minus A times D itself. So let me draw a cartoon of what this looks like. So we took our tiles and we took an enormous number of them and made a big set in the universal cover. And then we have the tiles that are attached to them, but which are not actually part of this set A times D. But since S included all of the tiles adjacent to D, S times D, S times A times D, this slight thickening corresponding to the boundary of A, this is the boundary of A times D, forms a neighborhood of AD of some definite width. And now out here we make our function 0, here we make our function 1, and here we make the function go down linearly from 1 to 0. And the point is that there is a definite width to this corona that we've drawn around D. So each of these, there's a small neighborhood, small radius r, that's contained in this corona, in this boundary set of boundary tiles. And so what can we say about the norm of F and the norm of the gradient of F? Well, the norm of F, squared is greater than or equal to the number of tiles in A times the volume of D. So let's normalize so that the volume of M, which is the same as the volume of D, is 1. So then the norm of F squared is just greater than or equal to the number of tiles in A. On the other hand, what about the norm of the gradient of F squared? Well, the gradient of F is O of 1 everywhere, because it's bounded on these tiles because you have a definite amount of room to go down from 0 to 1. And so the gradient is controlled by the number of tiles here, each of which has volume 1, and that's the size of the boundary of A. So the gradient of F is less than or equal to the size of the boundary of A. And so the ratio of one to the other is the ratio of the boundary of A to A, which is less than epsilon. So then we've constructed an F, a smooth function with compact support on M, such that the norm of the gradient of F squared over the norm of F squared is less than epsilon, and epsilon was arbitrary, so this implies lambda naught of M tilde is equal to 0. Okay, so that shows that this Laplacian is a reasonable proxy for these isoparametric constants, and that the study of the eigenvalues of the Laplacian is certainly tied up with the notion of non-amenability. Now, how can we make a similar argument which will give us expansion? Well, to get expansion, we have to take a sequence of groups. So for the expansion, study of expansion, we start with M, a compact manifold. G is pi 1 of M. And what we do is we take a sequence of finite Galois covers of M. So these are also compact since they're finite covers, and they're defined by giving a map from the fundamental group of M to this finite group Gn. And let's assume that the degree of the covers, which is the cardinality of Gn, goes to infinity. Now, of course, since M is compact, G is finitely generated, so we can attach to each of these Gn's a finite generating set and form the associated graphs. Gn, which are, I can just write as Gn comma S, the graph associated to Gn with the generating set S acting on it. And now the theorem is that we have inf over n of lambda 1 of mn is greater than 0 if and only if the Gn form a sequence of expanders. Okay, so the proof is almost exactly the same as the proof we just gave, at least in one direction. So this direction is easy. If these did not form a sequence of expanders, we could find some nice tilings of these MNs to give functions of mean 0 with small gradient, and that would contradict the fact that lambda 1 is bounded below. So what this theorem is telling us is that if we can find a natural sequence of manifolds where the bottom of the spectrum of the Laplacian, excluding the constants, is uniformly bounded below, then we're in good shape. Now I want to point out that when you take a finite cover of a manifold, the bottom of this lambda 1 usually goes down. For example, if you take a circle and you cover it by a much larger circle, then the smallest eigenfunction of the Laplacian, it corresponds to like a very slow sine wave up here, which you didn't have down here, right? So as you take larger and larger covers of circles, lambda 1 just goes to 0. It's challenging to construct a sequence of covers where lambda 1 stays bounded below. Lambda 1 always decreases because you can take an eigenfunction down here and pull it back. But there might be new eigenfunctions with lower Ritz-Rayleigh quotient, which are not invariant under these GNs. And so just to make a long story short and finish for today, there's a theorem we're going to quote due to Selberg that says the following: if you take the map from SL2Z to SL2Z mod P, and you take its kernel, which I'll call gamma of P, the matrix is congruent to the identity mod P, then lambda 1 of gamma P mod H is greater than or equal to 3/16 for all. And this theorem leads to the theorem that the graphs associated to SL2 FP give expanders. Okay, so that's the large scale narrative arc. And modulo this theorem, the proof is almost complete. The one thing that's wrong with the proof is this. This quotient space is not compact. As we know, the quotient of the upper half line by SL2Z has a cusp. It's finite volume, but not compact. Similarly, none of these covering spaces are compact. And so this theorem cannot be quoted verbatim. There has to be some sort of analysis carried out to deal with the finite volume case. What I'll do next time is explain how that's done. That will give these expanders for SL2, and then we'll move on to Kashtan's property T and the expanders for SL and Z for all Z. Okay.